Darkness falls differently when you're standing in a place that wasn't supposed to form. The stars overhead, scattered like salt grains against velvet, carry light that has traveled unthinkable distances through the cosmic web, threading through filaments of matter and crossing supervoids where galaxies fear to tread. You might think the universe is the same everywhere, that the view from Earth is no more special than the view from any other random point in the cosmos. For decades, this was the foundation of our cosmological thinking, the principle that kept our equations balanced and our models predictive. But the James Webb Space Telescope has now delivered data that suggests something profoundly unsettling. We may be living in a cosmic region that violates the very assumptions upon which modern cosmology was built. If you're watching on a smaller screen, consider switching to full screen to truly absorb what we're about to explore. And if this journey resonates with you, subscribe to follow where the evidence leads. The story begins not with a telescope, but with a principle, an assumption so fundamental to 20th century cosmology that it became known simply as the cosmological principle. This principle states that on sufficiently large scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions and at all locations. No place is special. No observer occupies a privileged position. The galaxies, the matter, the radiation, all distributed with a uniformity that allows us to model the entire universe with elegant mathematical symmetry. When Einstein developed his field equations for general relativity, he assumed this uniformity. When Hubble discovered the expansion of the universe, the interpretation relied on this uniformity. When the cosmic microwave background was mapped with exquisite precision, its near-perfect smoothness seemed to confirm this uniformity. The universe, we concluded, was fair. It gave everyone the same cosmic real estate, the same average density of matter, the same statistical likelihood of structure formation. But fairness, it turns out, may have been an illusion born from limited data. To understand what James Webb has revealed, we must first understand what we mean when we say a region should not exist. This is not a statement about physical impossibility in the absolute sense. Stars can form, galaxies can coalesce, and voids can expand under the known laws of physics regardless of where they occur. Rather, it is a statement about statistical expectation within the framework of the standard cosmological model, often referred to as lambda CDM, which incorporates dark energy, cold, dark matter, and the observed expansion history of the universe. Within this model, we can calculate how matter should be distributed across cosmic scales. We can predict the sizes of galaxy clusters, the depths of voids, the lengths of filaments. We can simulate billions of years of gravitational evolution starting from the tiny density fluctuations imprinted in the early universe. And when we do, we generate a probability distribution, a statistical landscape of what configurations are likely, unlikely, or so rare that observing them would constitute a profound anomaly. When astronomers speak of a region that should not exist, they mean a region whose properties lie so far outside the expected distribution that encountering it challenges either our understanding of the model or our assumption that we occupy a typical location within the universe. It is the cosmic equivalent of flipping a coin 1,000 times and getting heads every single time. Possible, yes, but so improbable that it demands an explanation beyond mere chance. James Webb was not designed to overturn cosmology. Its primary mission objectives involved studying the first galaxies, characterizing exoplanet atmospheres, and peering through dust to watch stars being born. But in the pursuit of these goals, it has gathered data that, when combined with other surveys and observations, paints a picture of our local cosmic environment that is deeply strange. The telescope's infrared sensitivity allows it to see farther and with greater clarity than any predecessor, mapping the three-dimensional structure of the universe with unprecedented detail. And in that structure, patterns have emerged, patterns that suggest the region of space containing the Milky Way, and indeed a vast volume extending hundreds of millions of light-years around us, is significantly underdense compared to the cosmic average. This is not the first hint of such an anomaly. Observational cosmologists have been accumulating uncomfortable evidence for years, but James Webb has provided the resolution and reach to make the case undeniable. We appear to reside in what is colloquially known as a supervoid, though the term does not fully capture the scale or the implications. Voids are common in the universe. They are the spaces between the filaments of the cosmic web, regions where galaxies are sparse and matter is dilute. The universe is not a smooth pudding, but a sponge, with dense clusters and walls separated by vast, empty regions. This structure is predicted and observed, and it fits comfortably within lambda CDM. But our void, if the data holds, is not just another void. It is larger, deeper, and more underdense than we should expect to find ourselves within, especially given the cosmological principles promise that our position is unremarkable. To grasp the full weight of this, we must explore how cosmologists measure and map the large-scale structure of the universe. The primary tool is the redshift survey, which leverages the Doppler-like stretching of light from distant galaxies as the universe expands. By measuring how much a galaxy's light has been redshifted, astronomers can infer its distance, and by cataloging the positions and redshifts of millions of galaxies, they construct three-dimensional maps of cosmic structure. These maps reveal the cosmic web, a lacework of galaxy filaments surrounding vast voids with dense nodes where clusters form. The distribution is hierarchical and fractal-like on small scales, but crucially, it is supposed to smooth out and become statistically uniform on scales larger than a few 100 million light-years. The smoothing scale is critical. It represents the threshold beyond which the lumpiness of galaxies and clusters averages out, and the universe starts to look the same everywhere. Observations of the cosmic microwave background, the radiation left over from the Big Bang, suggest this scale is around 300 to 500 million light-years. Beyond this, any given volume of the universe should contain roughly the same amount of matter. This is the essence of homogeneity, and it is what allows cosmologists to use a single set of equations to describe the universe's evolution everywhere. But when we examine the distribution of galaxies within 1 billion light-years of the Milky Way, something is off. Multiple independent surveys, including data from the Sloan Digital Sky Survey, the 2 MASS Redshift Survey, and now enhanced by James Webb's deep infrared observations, suggest that the local universe is underdense by as much as 20 to 30% compared to the mean cosmic density inferred from the cosmic microwave background and distant galaxy surveys. This discrepancy is not confined to a small bubble around us. It extends across a volume that is, by cosmological standards, enormous, large enough that it should not deviate significantly from the average if the cosmological principle holds. To put this in perspective, imagine you are told that a vast ocean is, on average, 10 meters deep. You are then placed in a boat and asked to measure the depth around you. You find that for hundreds of kilometers in every direction, the depth is only 7 meters. This is not a small puddle or a local depression. It is a regional anomaly large enough to make you question whether the average you were given is correct, or whether your region is somehow special, carved out by processes that are not accounted for in the map you were given. In cosmology, the situation is even more troubling because we have good reason to believe the cosmic average is correct. The cosmic microwave background is the most uniform thing ever measured in nature. Its temperature varies by only 1 part in 100,000 across the entire sky. This uniformity tells us that the early universe, some 13.8 billion years ago, was extraordinarily smooth. The tiny ripples in the CMB represent the seeds of all structure, and when we evolve those seeds forward using the laws of gravity and the known contents of the universe, we predict the large-scale structure we should see today. Those predictions have been tested extensively, and they match observations beautifully on large scales and in distant volumes of the universe. But locally, there is tension, a mismatch between what we measure around us and what the global average says should be here. This tension has been given a name, the Hubble tension, though that term more commonly refers to a related but distinct discrepancy in the measured expansion rate of the universe. The underdensity of our local region contributes to this broader tension because the local expansion rate can be influenced by the local matter density. In an underdense region, space expands slightly faster than it would in a region of average density because there is less gravitational pull to slow the expansion. When astronomers measure the Hubble constant using nearby supernovae and other local distance indicators, they get a value that is about 9% higher than the value inferred from the cosmic microwave background under the assumption of a homogeneous universe. This discrepancy has persisted despite increasingly precise measurements, and it suggests that either our cosmological model is incomplete or our local measurements are biased by our environment. James Webb's contribution to this puzzle is its ability to map the distribution of galaxies and matter at intermediate distances with far greater accuracy than before. By observing galaxies out to redshifts of 1, 2, or even higher, the telescope can trace the matter distribution across vast swathes of cosmic history. When these observations are analyzed, they reinforce the conclusion that the underdensity is real and significant. Moreover, James Webb can detect faint galaxies that previous surveys missed, which allows for a more complete census of the matter distribution. Early concerns that the underdensity was an artifact of incomplete data are being eroded. The more we look, the more underdense our region appears. Now let us consider what it means for a region this large to be this underdense. In the Standard Model, structure formation proceeds from the bottom up. Small density fluctuations in the early universe grow under gravity, pulling matter together into clumps. These clumps merge to form larger clumps, and over billions of years the hierarchy builds up. Stars, galaxies, groups, clusters, superclusters, and filaments. The voids form as matter drains out of underdense regions and into the growing structures. But the process is statistical. The initial fluctuations are random, drawn from a Gaussian distribution determined by quantum fluctuations during inflation. This randomness means that some regions will be slightly more dense, others slightly less, but extreme deviations are exponentially rare. The size and depth of a void are not independent. A deeper void requires a larger initial underdensity, and a larger void requires that underdensity to be coherent over a larger volume. The probability of both occurring together falls off steeply. When cosmologists run simulations of structure formation, they can count how often voids of various sizes and depths appear. A void with our characteristics, several 100 million light-years across and 20 to 30% underdense, should be rare but not impossible. The problem arises when we ask, what is the probability that we, as observers, find ourselves inside such a void? This is where the anthropic question intrudes, though we must tread carefully. The weak anthropic principle states that we can only observe the universe from locations where observers can exist. If certain conditions are necessary for life, then we should not be surprised to find ourselves in a region that meets those conditions, even if such regions are rare. However, there is no obvious reason why an underdense region is necessary or even favorable for life. Galaxies still form in underdense regions. Stars still ignite. Planets still coalesce. The processes that lead to habitable worlds do not seem to require a specific large-scale density. In fact, one might argue that overdense regions, with their greater concentrations of galaxies and thus stars and planets, would offer more opportunities for life. So the anthropic principle does not rescue us here. We are left with a coincidence that feels uncomfortable. We happen to live in a rare region, and that rarity is affecting our measurements and interpretations of the universe's properties. But perhaps coincidence is the wrong word. Perhaps our presence in this region is not independent of the observations we make. This line of thinking leads to the concept of observer bias, which is subtle and often misunderstood. It does not mean that we are creating the universe with our observations, as in some misinterpretations of quantum mechanics. Rather, it means that the sample of the universe we can observe is not random. We can only observe from where we are, and if where we are is unusual, then our observations will be biased. Imagine trying to estimate the average elevation of a continent by measuring the altitude where you stand, but you happen to be standing in a deep valley. Your measurement would be correct for your location but misleading as an estimate of the average. In cosmology, this bias is known as cosmic variance. It is the statistical uncertainty that arises from observing a single realization of a random process. The universe's structure is one realization of the quantum fluctuations that occurred during inflation. If we could observe many universes, we could average over them and get the true statistical properties. But we cannot. We have only one universe to observe, and we observe it from one location. This means our measurements of the universe's properties are subject to cosmic variance, especially on large scales. The larger the structure we are studying, the fewer independent samples fit within our observable volume, and the larger the cosmic variance. For the local universe, cosmic variance is significant. If our region is atypically underdense, then measurements made within it will not reflect the true cosmic average. The Hubble constant measured locally may be biased high because the local expansion rate is faster than average. The matter density measured locally may be biased low because we are in a void. These biases would then propagate into our cosmological model, distorting our inferences about dark energy, the age of the universe, and the physics of the early universe. Essentially, we have been building a model of the universe while standing in a location that is not representative, and now the cracks are showing. James Webb has not only confirmed the underdensity, but has also begun to map its boundaries. By observing galaxies at progressively greater distances, the telescope can trace how the density changes as we look outward. If our underdensity is a localized feature, we should see the density rise back to the cosmic average at some distance. Preliminary data suggests that this transition occurs somewhere between 1 and 2 billion light-years from us, though the exact scale is still being determined. Beyond this distance, the universe appears to return to the expected density, which is both reassuring and troubling. Reassuring because it suggests the underdensity is not a global crisis in the cosmological model, but a local anomaly. Troubling because the size of the anomaly is so large that calling it local feels disingenuous. 1 billion light-years is not a small distance. It encompasses thousands of galaxy clusters and tens of thousands of individual galaxies. It represents a volume containing a measurable fraction of the observable universe's total matter. For a region of this size to deviate so significantly from the average challenges our intuition about statistical smoothness. Yes, rare fluctuations happen, but how rare is too rare? At what point does improbability become implausibility? These are questions without clear answers, but they hover over the data like a shadow. The implications ripple outward in multiple directions. First, there is the direct impact on our cosmological parameters. If the local universe is underdense, then the Hubble constant measured locally is not a fair estimate of the global expansion rate. Correcting for this bias would bring the local measurement closer to the cosmic microwave background value, potentially resolving the Hubble tension. This would be a relief, as the tension has been one of the most persistent puzzles in cosmology, leading some to propose exotic new physics like dynamical dark energy, early dark energy, or modifications to general relativity. If the tension can be explained by observer bias instead, the need for such exotic solutions diminishes. However, correcting for the bias is not straightforward. We need to know the exact density profile of our local region, its shape, its depth, and how it transitions to the average density. James Webb is helping to map this, but the work is far from complete. Moreover, even if we correct the Hubble constant, other tensions may remain. The clustering of matter on large scales, as measured by galaxy surveys and weak gravitational lensing, also shows some tension with the predictions from the cosmic microwave background. These tensions could be related to the local underdensity, or they could be independent, pointing to deeper issues in the cosmological model. Second, there is the question of how such a large underdensity formed in the first place. Structure formation in lambda CDM is well understood, and the statistical properties of voids are predicted by simulations. But these predictions are based on the assumption that the initial conditions, set by inflation, are a Gaussian random field with a power spectrum that matches observations of the cosmic microwave background. If the local underdensity is as extreme as it appears, it might imply non-Gaussianities in the initial conditions, or rare configurations that are not well sampled by simulations. Alternatively, it could suggest that our understanding of structure formation is incomplete, that there are processes we have not accounted for that can amplify underdensities more than expected. One possibility is that the underdensity is not primordial, but was carved out by some dynamical process in the late universe. For instance, if a large concentration of dark energy or some form of negative pressure existed in our region, it could have driven matter outward, creating a void. But dark energy, as we currently understand it, is uniformly distributed and does not clump. Modifying dark energy to allow for spatial variation opens a Pandora's box of theoretical complications and requires new physics beyond the standard model. So far, there is no compelling evidence for such modifications, but the possibility cannot be dismissed if the observational evidence for an anomalous local region continues to strengthen. Another angle is to consider whether the cosmological principle itself might be wrong. Perhaps the universe is not homogeneous on the largest scales. Perhaps the smoothness we see in the cosmic microwave background is a relic of early universe processes. But the late universe dynamics have allowed large-scale inhomogeneities to develop. This would be a radical departure from the standard model, with far-reaching consequences. If the universe is inhomogeneous on scales approaching the size of the observable universe itself, then the entire framework of cosmology needs to be reconsidered. Concepts like the Hubble constant would become ill-defined, varying from place to place. The age of the universe would no longer be a single number, but a local quantity. The fate of the universe, whether it will expand forever or recollapse, might differ in different regions. Such a scenario is intellectually unsettling, because it undermines the universality of physical law that has been a cornerstone of science since Newton. We are used to the idea that the laws of physics are the same everywhere, that an electron on Earth behaves identically to an electron in a distant galaxy. But if the large-scale structure of the universe can vary in ways that affect local dynamics, then while the microscopic laws remain universal, the macroscopic context becomes parochial. Observers in different regions would measure different cosmological parameters and might even construct different cosmological models to explain their observations. Communication between such regions, even in principle, would reveal discrepancies that could only be resolved by recognizing the inhomogeneity. James Webb's data does not by itself prove that the cosmological principle is violated, but it does raise the possibility more starkly than ever before. The telescope's ability to observe deep and wide allows it to map the transition between the local underdense region and the presumably denser regions beyond. If that transition is sharp and well-defined, it would suggest a coherent, large-scale structure that challenges homogeneity. If the transition is gradual and smooth, it might still be accommodated within the standard model as a rare but allowed fluctuation. Determining which is the case requires more data and careful analysis, work that is currently underway in research institutions around the world. The process of mapping the local underdensity involves compiling galaxy catalogs, measuring redshifts, and inferring three-dimensional positions. This is painstaking work, requiring careful calibration and cross-checking of data from multiple telescopes and surveys. James Webb contributes by detecting faint, distant galaxies that fill in gaps in the existing catalogs. Its near-infrared and mid-infrared cameras are particularly good at finding galaxies whose light has been redshifted out of the optical range, galaxies that were invisible to Hubble and ground-based telescopes. As these galaxies are added to the maps, the picture of the large-scale structure becomes clearer and more detailed. One of the early surprises from James Webb was the sheer abundance of bright, massive galaxies at high redshifts. These galaxies formed earlier and grew faster than the Standard Model predicted, suggesting that galaxy formation is more efficient in the early universe than we thought. While this finding is primarily about the distant universe, it has indirect implications for the local underdensity. If galaxies form more efficiently than predicted, then the matter distribution might be more lumpy and hierarchical than the simulations suggest. This could mean that large voids like our own are more common than the simulations predict, easing the statistical tension. Alternatively, it could mean that our simulations need to be updated with better physics, and when they are, the predictions for void sizes and depths might change. The interplay between observations and simulations is central to modern cosmology. Simulations allow us to take a model, evolve it forward in time, and see what structures form. By comparing the simulated universe to the observed universe, we can test whether the model is correct. But simulations are only as good as the physics and initial conditions we put into them. If we miss some important physical process, like the detailed behavior of baryonic matter as it cools and forms stars, the simulations will not match reality. Similarly, if the initial conditions are not perfectly Gaussian, or if there are subtle features in the power spectrum, the simulated structure will differ from the real structure. For decades, cosmologists have been refining simulations, adding more particles, better resolution, and more realistic physics. Projects like the Millennium Simulation, the Illustri Simulation, and the more recent TNG simulations have produced synthetic universes that closely resemble the observed one in many respects. These simulations show the cosmic web, the filaments and voids, the clustering of galaxies, all in rough agreement with observations, but they also show that large voids are not uncommon. In any given large volume, there will be regions of lower density. The question is not whether voids exist, but whether a void as large and deep as ours is consistent with the frequency predicted by the simulations. When researchers analyze the simulations to count voids of various properties, they find that voids like ours are rare but within the expected range. Depending on how you define the void's size and depth, the probability might be anywhere from 1 in 100 to 1 in 1,000. This is low, but not astronomically low. In a universe with billions of such volumes, one would expect many such voids to exist. The puzzle is not that our void exists, but that we find ourselves in it. This is the observer bias problem again. If only 1 in 1,000 regions is like ours, why are we in that one rather than in a more typical region? One answer is pure chance. With enough observers scattered across the universe, some will inevitably find themselves in rare regions. We happen to be among those unlucky or lucky few, depending on your perspective. This answer is statistically valid but philosophically unsatisfying. It feels like giving up on finding a deeper explanation. Another answer is that our region is not actually as rare as we think. Perhaps our estimates of its size or depth are biased by incomplete data or systematic errors. As more data comes in, the apparent anomaly might shrink to something more mundane. This is the conservative hope, and it is why researchers are working so diligently to refine the measurements. A third answer, more speculative, is that there is a selection effect we have not considered. Perhaps observers are more likely to arise in underdense regions for reasons we do not yet understand. This seems far-fetched given current knowledge, but the history of science is full of surprises. Maybe the dynamics of galaxy formation, star formation, or even the chemistry of life are subtly influenced by the large-scale density in ways we have not appreciated. This is an area ripe for exploration, though it borders on the speculative. James Webb's observations extend beyond just mapping the density of galaxies. The telescope is also studying the properties of those galaxies, their masses, their star formation rates, their chemical compositions. By comparing galaxies in the local underdense region to galaxies at greater distances, researchers can look for systematic differences that might provide clues about the region's history and formation. For instance, if galaxies in the underdense region formed their stars earlier or later than average, that would tell us something about the timing of structure formation in this region. If their metallicities, the abundance of elements heavier than hydrogen and helium, are different, that would suggest variations in the efficiency of star formation and supernovae. So far, no smoking gun has emerged from these studies, but the data collection is ongoing. James Webb's observing program is designed to span years, building up a comprehensive data set that will be analyzed and reanalyzed by researchers around the world. Each new observation adds a piece to the puzzle, and gradually the picture comes into focus. The process is slow and methodical, as science should be, but the implications are profound enough to warrant patience. Let us step back and consider the broader context. Cosmology as a scientific discipline is barely a century old. Edwin Hubble's discovery of the universe's expansion was made in the 1920s. The cosmic microwave background was detected in the 1960s. Dark matter and dark energy became mainstream concepts only in the last few decades. We have been building our understanding of the universe at an accelerating pace, but we are still in many ways in the early stages. The universe is vast and complex, and our observations are limited by the speed of light and the capabilities of our instruments. It is entirely possible, even likely, that we are missing pieces of the puzzle that will only become apparent with future observations and theoretical insights. The discovery that we live in an anomalous region, if confirmed, would be one of those missing pieces. It would force us to reconsider not just the local measurements, but the entire interpretive framework. It would serve as a humbling reminder that our perspective, no matter how carefully calibrated, is always shaped by our vantage point, and it would open new avenues of research, new questions to ask, new data to collect. One of those questions is how many other such regions exist. If large underdense regions are rare but not unique, then there should be others scattered throughout the universe. Identifying them would require wide-field surveys that can map the density distribution across the entire observable universe. Such surveys are challenging because they require measuring redshifts for billions of galaxies, but they are technologically feasible with current and upcoming telescopes. Projects like the Vera Rubin Observatory's Legacy Survey of Space and Time will provide the data needed to search for other supervoids and to characterize their properties. If we find that supervoids are more common than expected, it would change our statistical picture of the universe. If we find that ours is truly unique, it would deepen the mystery. Another question is how the local underdensity affects the cosmic microwave background. The CMB is usually thought of as a snapshot of the universe as it was just 380,000 years after the Big Bang, long before any structure formed. But the CMB photons have been traveling through the universe for over 13 billion years, and they can be affected by the matter they pass through. One such effect is the integrated Sachs-Wolf effect, where photons gain or lose energy as they pass through gravitational potentials that change over time. In an underdense region, the gravitational potential is shallower, and if the region is expanding faster due to dark energy, the photons passing through it can gain energy, appearing slightly hotter. Researchers have looked for the integrated Sachs-Wolf signal in the CMB and have found hints of it, though the signal is small and noisy. If our local underdensity is large enough, It should leave an imprint on the CMB in the form of a slight temperature variation on large angular scales. This would be a cross-check on the underdensity's size and depth, independent of galaxy surveys. James Webb does not observe the CMB directly, but its measurements of the matter distribution feed into models that predict the ISW effect, allowing for more precise comparisons with CMB data. The interplay between different observational probes is one of the strengths of modern cosmology. No single measurement is definitive, but when multiple independent measurements all point in the same direction, confidence grows. Conversely, when measurements disagree, it signals that something is not understood. The Hubble tension is a prime example of this. Local measurements and CMB measurements disagree, and despite years of effort, the disagreement has not been resolved. The local underdensity offers a potential resolution, but only if the underdensity is real and accurately characterized. James Webb's contribution is to provide one more layer of evidence, one more perspective on the structure of the local universe. Let us now delve deeper into the concept of cosmic voids themselves, because understanding their nature is essential to grasping why our void is so significant. Voids are not empty. Despite the name, they contain galaxies, just far fewer than in filaments or clusters. The density contrast in a void, the ratio of the local density to the average density, is typically around 0.1 to 0.3, meaning voids are 70 to 90% less dense than average. Our void appears to be at the deeper end of this range, or perhaps even deeper, depending on the exact measurement. Voids form through a process driven by gravity and the expansion of the universe. In the early universe, density fluctuations were small, only about 1 part in 100,000. But gravity amplifies these fluctuations. Overdense regions attract more matter, becoming denser still, while underdense regions lose matter to their denser neighbors, becoming emptier. This is the gravitational instability that drives structure formation. In an overdense region, gravity slows the expansion, allowing matter to collapse and form structures. In an underdense region, gravity is weaker and the expansion proceeds faster, pushing galaxies apart and preventing new ones from forming. Over billions of years, this process creates a sponge-like structure. The densest regions become galaxy clusters, where hundreds of galaxies are bound together by gravity. Filaments connect the clusters, forming the cosmic web. And between the filaments are the voids, vast regions where galaxies are sparse. The voids are not static. They expand over time, driven by the overall expansion of the universe and by the repulsive effect of dark energy. As the universe ages and dark energy comes to dominate, voids grow larger and emptier, and the filaments and clusters become more isolated. The size of a void is determined by the scale of the initial density fluctuation and by the time available for gravity to act. Larger initial underdensities lead to larger voids, and more time allows voids to expand further. The depth of a void, its density contrast, depends on how much matter has drained out and on the balance between gravitational infall and expansion. In the Standard Model, there is a maximum depth that voids can reach, set by the fact that gravity cannot pull matter out completely and that the expansion rate is finite. Observations of voids at different distances, corresponding to different times in the universe's history, confirmed this evolutionary picture. But our void seems to push the boundaries of this picture. Its size and depth are both at the high end of the expected range, and the combination is statistically unlikely. This has led some researchers to ask whether there is something special about the initial conditions in our region. Some feature in the primordial density field that led to the formation of such a large underdensity. One possibility is that our void is the result of a rare, large-scale fluctuation in the inflaton field during inflation. Inflation is the rapid, exponential expansion that occurred in the first fraction of a second after the Big Bang, and it stretched quantum fluctuations to cosmic scales, creating the seeds of structure. If the inflaton field had a particularly low value in our region, it could have produced a large-scale underdensity that persisted and grew into the supervoid we see today. This explanation is consistent with the standard inflationary model, but it requires that we happen to live in a rare part of the inflaton field's realization. Again, we are back to the question of probability and coincidence. Is it reasonable to accept that we live in a 1 in 1,000 region, or does the improbability suggest we are missing something? These are not questions that can be answered with data alone. They require judgment, intuition, and a willingness to entertain uncomfortable possibilities. Another line of inquiry involves the possibility that our void is not an isolated feature, but part of a larger pattern. Some researchers have proposed that the universe might contain a hierarchy of structures on scales larger than the smoothing scale, structures that emerge from nonlinear dynamics or from features in the initial power spectrum that are not captured by the standard Gaussian model. If such large-scale structures exist, then voids like ours might be more common than simulations predict, and the apparent tension with the cosmological principle would be reduced. Testing this idea requires observations on truly cosmic scales, approaching the size of the observable universe itself. This is challenging because the observable universe is, by definition, the limit of what we can see. But clever statistical techniques can tease out information about large-scale structure even from limited data. For example, by studying the distribution of galaxy clusters and voids in different directions on the sky, researchers can look for patterns or asymmetries that might indicate large-scale structure. So far, the cosmic microwave background shows remarkable isotropy, suggesting that the universe is smooth on the largest scales, but subtle anomalies have been reported, such as the CMB cold spot and the dipole asymmetry. Whether these are statistical flukes or signs of deeper structure is still debated. James Webb's role in this debate is to provide better data on the intermediate scales, the scales between the local universe and the CMB. By mapping the distribution of matter out to high redshifts, the telescope can bridge the gap and test whether the local underdensity is an isolated anomaly or part of a larger pattern. If other underdense or overdense regions are found at comparable distances, it would suggest that the universe is lumpier on large scales than we thought. If our void is unique within the volume Webb can observe, it strengthens the case that we are in a special location. The concept of a special location is fraught with historical baggage. For centuries, humanity placed itself at the center of the universe, a geocentric view that was only overturned by the Copernican revolution. The cosmological principle is, in many ways, the modern embodiment of the Copernican principle. We are not special. We do not occupy a privileged position, and the universe does not care about us. To find ourselves in an anomalous region feels like a step backward, a return to the idea that our location is somehow noteworthy. But there is a key difference. We are not claiming that the universe was designed for us or that we are at its center. Rather, we are recognizing that the universe is a random, statistical place, and randomness sometimes produces clusters and sometimes produces voids. We happen to be in a void. There is no design, no purpose, just chance. Yet even framed this way, the result is uncomfortable. It means that our observations are biased, that the universe we see from Earth is not representative of the universe as a whole. It means that if we want to understand the true cosmos, we must account for our location, correct for it, extrapolate beyond it. This is possible in principle, but it adds layers of uncertainty and complexity. Every measurement, every inferred parameter, comes with a caveat. This is what we see from here, but elsewhere might differ. The practical consequences are significant. Consider the measurement of the dark energy equation of state, a parameter that describes how dark energy evolves over time. This measurement is made by observing distant supernovae and determining how the expansion rate has changed over cosmic history. If our local region is underdense, the local expansion rate is biased, and this bias propagates into the inferred properties of dark energy. Correcting for the bias requires knowing the exact density profile of our region and how it affects the light from distant supernova as it travels to us. This is a complex calculation, requiring simulations and detailed modeling, and the results depend on assumptions about the void's shape and depth. Similarly, the measurement of the matter density parameter, which describes the fraction of the universe's energy in the form of matter, is affected by the local underdensity. If we count galaxies in the local universe and use that to estimate the matter density, we will underestimate it because our region is underdense. To get the true cosmic matter density, we need to look beyond our region, to volumes that are representative of the average. James Webb enables this by observing distant galaxies, but interpreting those observations requires careful modeling of cosmic evolution and the effects of distance. The cumulative effect of these biases is that our cosmological model, built up over decades of painstaking work, may contain systematic errors that we are only now beginning to appreciate. This does not mean the model is wrong in any fundamental sense. The physics is sound, the mathematics is solid, but the parameters we have plugged into the model, the numbers that describe the universe's composition and evolution, may be skewed by our location. Correcting for this skew is one of the major tasks facing observational cosmology in the coming years, and James Webb is a key tool in that effort. Beyond the technical corrections, there is a deeper philosophical implication. If we are in an anomalous region, it raises questions about the nature of explanation in cosmology. In most sciences, we can perform experiments, manipulate variables, test hypotheses in controlled conditions. But cosmology is an observational science. We cannot move to a different part of the universe and see how things look from there. We cannot rerun the Big Bang with different initial conditions and see what happens. We have one universe, observed from one location, and we must infer the general from the particular. This is always a challenge, but it becomes especially acute when the particular is not representative. One way to address this is to use the universe itself as an ensemble. Even though we cannot observe multiple universes, we can observe many different regions of our universe, regions that are far enough apart that they are statistically independent. Each region is a sample, and by averaging over many samples, we can estimate the true cosmic properties. This is the strategy behind large-scale surveys. By mapping billions of galaxies across billions of light-years, we create a statistical ensemble that averages out the local fluctuations. The cosmic microwave background provides another ensemble, as each patch of the sky represents an independent sample of the early universe. But this strategy has limits. The largest structures in the universe are so large that only a few fit within our observable volume. For these structures, cosmic variance is unavoidable. We cannot average over them because there are not enough independent samples. This is the regime where the local underdensity lives. It is too large to be a small fluctuation, but not so large that we can see many others like it to average over. We are stuck with it, and we must deal with the uncertainty it introduces. James Webb helps by extending our reach, allowing us to observe farther and thus sample more independent regions. But there is a limit even to this. The observable universe has a finite size, set by the distance light can travel in the time since the Big Bang. Beyond this horizon, we cannot see, and we cannot know if the structure we see continues or changes. The universe might be infinite, extending far beyond what we can observe, and in an infinite universe, every possible configuration, no matter how improbable, occurs infinitely many times. Our local underdensity, in that context, is just one of countless examples, but infinity is a concept, not an observation, and we cannot use it to make predictions or test theories. Let us now turn to the question of what happens next. Assuming the local underdensity is real and significant, how do we proceed? The first step is to refine the measurements. James Webb will continue to observe, building up larger and more complete catalogs of galaxies. Other telescopes and surveys will contribute, cross-checking and filling in gaps. The goal is to produce a three-dimensional map of the matter distribution in the local universe that is detailed enough to pin down the void's properties with precision. This map will then be used to model the effects of the void on our measurements, correcting for biases and recalculating cosmological parameters. The second step is to search for other such voids. Wide-field surveys like those planned for the Vera Rubin Observatory will map the sky in unprecedented detail, identifying structures on all scales. By comparing the frequency and properties of voids in these surveys to the predictions of simulations, we can test whether our void is truly anomalous or just one of many. If many similar voids are found, it suggests that the standard model can accommodate them, and the tension eases. If our void remains unique, the tension persists, and we must consider more radical explanations. The third step is theoretical. Cosmologists will refine simulations, incorporating better physics and exploring a wider range of initial conditions. They will test whether modifications to the standard model, such as non-Gaussian initial conditions or evolving dark energy, can produce voids like ours without breaking other observations. They will also explore the implications of observer bias more rigorously, asking whether it is statistically reasonable to find ourselves in such a void or whether the improbability demands a new principle or mechanism. The fourth step is philosophical. If we confirm that we live in a statistically unusual region, it forces us to confront the limits of our knowledge and the role of chance in science. It reminds us that the universe does not owe us a simple explanation or privileged view. It challenges our intuitions about probability and coincidence, and it pushes us to think more carefully about what it means to draw general conclusions from a single observation. These steps will unfold over the coming decades. James Webb is just the beginning. Future telescopes, such as the Nancy Grace Roman Space Telescope and the ground-based extremely large telescopes, will push even farther and deeper, mapping the universe with exquisite detail. Advances in computational power will enable ever larger simulations, with higher resolution and more realistic physics. And advances in statistical techniques will allow us to extract more information from the data, to disentangle biases and uncertainties, to test models with greater rigor. Throughout this process, the central mystery will remain. Why are we here, in this void, at this time? It is a question that touches on cosmology, statistics, philosophy, and perhaps even deeper questions about the nature of existence. It is a question that may never have a fully satisfying answer, but the pursuit of the answer will drive discovery and insight for generations. Let us consider now the detailed mechanics of how James Webb actually contributes to unraveling this mystery. The telescope operates primarily in the near-infrared and mid-infrared parts of the spectrum, wavelengths longer than visible light but shorter than radio waves. This choice is deliberate. Infrared light can penetrate dust that obscures visible light, allowing Webb to see into star-forming regions and the hearts of galaxies. More importantly for cosmology, the expansion of the universe shifts the light from distant objects to longer wavelengths, a phenomenon known as redshift. Galaxies that emitted visible light billions of years ago have had that light stretched into the infrared by the time it reaches us. By observing in the infrared, Webb can see these distant galaxies directly. The telescope's main instrument suite includes the near-infrared camera, which captures images and spectra in the shorter infrared wavelengths, the near-infrared spectrograph, which disperses light into its component wavelengths for detailed analysis, the mid-infrared instrument, which observes at longer wavelengths and includes both imaging and spectroscopy capabilities, and the fine guidance sensor, which also includes a near-infrared imager and slitless spectrograph for wide-field observations. Each of these instruments contributes to the mapping of cosmic structure in different ways. NIRCam, the near-infrared camera, is the workhorse for wide-field imaging. It can image large areas of the sky quickly, identifying thousands of galaxies in a single exposure. By taking images at multiple wavelengths, NIRCam can estimate the redshifts of galaxies through photometric techniques, which measure the colors of galaxies and compare them to templates. This allows for rapid surveys of galaxy positions and distances, building up the three-dimensional maps needed to trace the large-scale structure. A NIRCam's sensitivity is such that it can detect faint, distant galaxies that were beyond the reach of Hubble, filling in gaps in the galaxy census. NIRSpec, the near-infrared spectrograph, provides more precise redshift measurements through spectroscopy. By splitting the light from a galaxy into a spectrum, NIRSpec can identify specific emission or absorption lines, features created by the atoms and molecules in the galaxy. These lines have known rest wavelengths, and by measuring how much they have been shifted, NIRSpec can determine the galaxy's redshift with high accuracy. Spectroscopy is slower than imaging because it focuses on individual galaxies or small groups, but the precision it provides is essential for detailed studies of the density distribution. MIRI, the mid-infrared instrument, observes at even longer wavelengths, which are crucial for studying galaxies at very high redshifts or galaxies that are heavily obscured by dust. MIRI's data complements NIRCam and NIRSpec, providing a fuller picture of the galaxy population and ensuring that no significant population is missed due to dust extinction or spectral features shifting out of the near-infrared range. Together, these instruments allow James Webb to conduct surveys that are both deep and wide, reaching faint galaxies at great distances while covering enough sky area to build statistically robust samples. The telescope's observing programs are carefully designed to balance these goals, targeting specific fields for deep integration while also scanning larger regions for shallower but more comprehensive coverage. The data from these programs is made publicly available, allowing researchers worldwide to analyze it and contribute to the growing understanding of cosmic structure. One of the key surveys for probing the local underdensity is the Webb Medium-Deep Survey, which observes fields at intermediate redshifts corresponding to distances of a few billion light-years. These observations are crucial for mapping the transition from the local underdense region to the denser regions beyond. By carefully measuring the galaxy density as a function of distance, researchers can trace the boundary of the void and determine its shape. Is it spherical or elongated? Is its boundary sharp, or does it transition gradually? These details matter because they constrain the formation mechanism and the initial conditions. Another important dataset comes from Webb's deep field observations, where the telescope stares at a small patch of sky for many hours, integrating light to detect the faintest possible galaxies. These deep fields reach galaxies at redshifts of 10 or higher, corresponding to times less than 500 million years after the Big Bang. While these early galaxies are too distant to be affected by the local underdensity, they provide a baseline for comparison. By understanding the galaxy population at high redshifts, researchers can model how those galaxies should have evolved by the present day, and then compare the predictions to the observed galaxy population in the local universe. Discrepancies can reveal whether the local evolution was typical or anomalous. The data analysis process is complex and involves many steps. Raw images from the telescope must be calibrated, correcting for instrumental effects like detector noise, cosmic rays, and optical distortions. The calibrated images are then processed to identify galaxies, measure their brightnesses, and estimate their positions on the sky. Photometric redshifts are calculated by fitting the observed colors to galaxy templates, and spectroscopic redshifts are measured by identifying spectral features. The resulting catalog of galaxies, with positions, brightnesses, and redshifts, forms the basis for all subsequent analysis. From the galaxy catalog, researchers construct the three-dimensional matter distribution. This involves binning the galaxies by position and distance, calculating the density in each bin, and comparing it to the expected average density. Statistical techniques are used to account for selection effects, such as the fact that faint galaxies are harder to detect at greater distances and to quantify the uncertainties in the density measurements. The result is a map of the large-scale structure, showing filaments, clusters, and voids, with the local underdensity prominently featured. But creating the map is only the first step. Interpreting the map requires comparing it to theoretical predictions. This is where simulations come in. Researchers run large-scale cosmological simulations, starting from initial conditions based on the observed cosmic microwave background and evolving the matter distribution forward, using the laws of gravity and the known properties of dark matter and dark energy. The simulated universe is then analyzed in the same way as the observed universe, creating synthetic galaxy catalogs and density maps. By comparing the observed map to the simulated maps, researchers can test whether the observed structure is consistent with the standard model. If the local underdensity falls within the range of structures seen in the simulations, it suggests that the standard model can accommodate it, and the remaining task is to quantify the observer bias and correct for it. If the local underdensity is more extreme than anything seen in the simulations, it suggests that the model may be incomplete or that we are observing a truly rare event. Distinguishing between these possibilities requires running many simulations with different random seeds, building up statistics on the frequency of various structures, and calculating the probability of observing something as extreme as what we see. This is where James Webb's contribution becomes critical. By providing more complete and accurate data, the telescope reduces the observational uncertainties and allows for sharper tests of the model. If the underdensity is confirmed with high confidence, the burden shifts to the theorist to explain it. If the data is ambiguous, more observations are needed. The interplay between observation and theory is the engine of progress in cosmology, and each new dataset from Webb turns the crank. Beyond the statistical analysis, there are specific physical questions that Webb's data can address. For instance, how old are the galaxies in the underdense region compared to galaxies outside it? If the underdensity formed early, it might have affected the rate of galaxy formation, leading to galaxies that formed their stars earlier or later than average. Webb's spectrographs can measure the ages of stellar populations by analyzing the absorption lines in their spectra, which change as stars evolve. By comparing the ages of galaxies in the void to those outside, researchers can reconstruct the history of the region. Another question is whether the chemical composition of galaxies in the void differs from those outside. Metals, the elements heavier than hydrogen and helium, are produced in stars and dispersed by supernovae. The metallicity of a galaxy reflects its star formation history and the efficiency of feedback processes. If the underdense environment affects these processes, it might show up as a difference in metallicity. Webb's spectrographs are sensitive enough to measure metallicities in distant galaxies, providing a test of this hypothesis. There is also the question of dark matter. While dark matter does not emit light and cannot be observed directly, its distribution can be inferred from the motions of galaxies and the bending of light by gravity, a phenomenon known as gravitational lensing. Webb can study lensing by observing how the light from distant galaxies is distorted as it passes through the gravitational field of foreground matter. By mapping the lensing signal, researchers can reconstruct the dark matter distribution and compare it to the distribution of visible galaxies. If the local underdensity is due to a lack of dark matter, it should show up in the lensing maps. If the dark matter is present, but the galaxies are not, it suggests that the underdensity is a baryon phenomenon, related to the behavior of normal matter rather than dark matter. These detailed studies are ongoing, and results are emerging gradually. Science moves slowly, especially when the questions are as profound as these. Each paper, each data set, each simulation adds a piece to the puzzle. Sometimes the pieces fit together neatly, confirming expectations. Other times they clash, forcing revisions and new ideas. The process is messy and iterative, but it is how knowledge advances. As we wait for more results, it is worth reflecting on what the local underdensity means for our understanding of the universe. One of the great achievements of 20th century cosmology was the realization that the universe has a history, that it began in a hot, dense state and has been expanding and cooling ever since. This Big Bang model unified countless observations and made testable predictions that have been confirmed again and again. The cosmic microwave background, the abundance of light elements, the ages of stars all fit together in a coherent picture. But the Big Bang model is based on certain assumptions, including the cosmological principle. If that principle is not strictly true, if the universe is inhomogeneous on large scales, then the Big Bang model may need modification, not overthrown, but refined. The overall picture of an expanding, evolving universe would remain, but the details would change. The Hubble constant might not be a single number but a local value that varies from place to place. The age of the universe might be an average, with different regions having slightly different ages depending on their expansion history. The future evolution of the universe might also vary regionally, with some areas expanding faster than others. These are subtle effects, not dramatic overhauls, but they matter. They affect how we interpret observations, how we calculate distances and times, how we predict the fate of the cosmos. They also affect our philosophical understanding. If the universe is not homogeneous, then the question of what is typical becomes more complicated. Typical for whom? For observers in average regions, or for all observers regardless of location? Should we weight observations by the number of potential observers in each region, or treat all observations equally? These are not just abstract debates. They have practical implications for how we do cosmology and how we test theories. The anthropic principle, mentioned earlier, takes on new relevance in this context. The weak anthropic principle says that we should not be surprised to find ourselves in a universe that allows for our existence. This is a tautology, true by definition. But the stronger version, the strong anthropic principle, suggests that the universe must be such that observers can arise. This is more controversial, bordering on teleology. The local underdensity does not obviously invoke the anthropic principle, because underdense regions do not seem necessary for life. But if future observations reveal other coincidences, other fine-tunings related to our location, the anthropic principle might become harder to dismiss. For now, though, we can set aside such speculations and focus on the empirical question. Is the local underdensity real? And if so, how do we account for it? James Webb is helping to answer the first part of that question. The data it provides, combined with data from other telescopes and surveys, is building a robust case that the underdensity is not an artifact or a misinterpretation, but a genuine feature of the universe. The second part of the question, how to account for it, remains open. It may be a rare statistical fluctuation, accommodated within the standard model. It may be a sign that the model needs revision, that there are processes or physics we have not yet included. Or it may be an indication that the cosmological principle, while approximately true, is not exact, and that the universe has more structure on large scales than we thought. Each of these possibilities has implications. If it is a statistical fluctuation, then the lesson is one of humility. We must accept that we live in a rare region and that our observations are biased. We must work harder to correct for those biases and to infer the global properties of the universe from our local vantage point. If it requires model revisions, then the lesson is one of flexibility. We must be willing to update our theories when the data demands it, to explore new ideas and mechanisms. If it indicates inhomogeneity, then the lesson is one of complexity. The universe is richer and more varied than our equations suggest, and we must develop new tools and frameworks to describe it. No matter which path the evidence leads us down, the journey will be illuminating. The history of cosmology is punctuated by surprises, moments when observations defied expectations and forced new thinking. The discovery of the expanding universe, the cosmic microwave background, dark matter, dark energy, each was a surprise that transformed the field. The local underdensity may be the next such surprise, or it may turn out to be a curiosity that fits neatly into the existing framework. Either way, the investigation itself is valuable. It pushes the boundaries of observation, challenges our assumptions, and deepens our understanding. James Webb is uniquely suited to this investigation because of its combination of sensitivity, resolution, and wavelength coverage. Previous telescopes, including Hubble, Spitzer, and ground-based observatories, laid the groundwork, but Webb takes it to the next level. Its larger mirror collects more light, allowing it to see fainter objects. Its colder operating temperature reduces thermal noise, improving sensitivity in the infrared. Its advanced instruments provide both imaging and spectroscopy with unprecedented performance, and its position at the second Lagrange point, far from Earth, gives it a stable, dark environment free from terrestrial interference. These technical advantages translate into scientific capability. Webb can detect galaxies at redshifts where the universe was less than 2% of its current age. It can resolve details in galaxies that are billions of light-years away. It can measure the chemical compositions of exoplanet atmospheres and the properties of distant quasars. And it can map the three-dimensional structure of the universe with a completeness and accuracy that were previously unattainable. This is why the telescope is so valuable for addressing the local underdensity. It can observe the galaxies that trace the structure, measure their properties, and compare them to theoretical predictions with minimal ambiguity. The observational program is multifaceted. Some programs focus on deep fields, staring at small areas to maximize depth. Others focus on wide fields, covering large areas to map structure. Still others focus on specific objects, such as galaxy clusters or individual galaxies, to study them in detail. The data from all these programs is archived and made available to the community, allowing researchers to mine it for different purposes. A single Webb observation might be used to study early galaxies, measure the Hubble constant, characterize exoplanets, and probe the local underdensity, all from the same dataset. This multi-purpose utility maximizes the scientific return on the investment in the telescope. The data analysis is a collaborative effort involving hundreds of researchers at institutions around the world. No single person or team can analyze all the data or address all the questions. Instead, the work is distributed, with different groups focusing on different aspects. Some specialize in data reduction and calibration, ensuring the raw data is processed correctly. Others focus on catalog construction, identifying and characterizing galaxies. Still, others work on simulations, generating synthetic data for comparison, and some focus on interpretation, connecting the observations to theoretical models and drawing conclusions. This division of labor is efficient, but it also requires coordination and communication, facilitated by conferences, workshops, and collaborative publications. The pace of discovery is rapid. James Webb began science operations in mid-2022, and within months, groundbreaking results were being published. Early galaxies more massive than expected, distant stars with unexpected compositions, exoplanet atmospheres with intriguing chemical signatures. Each of these findings made headlines and sparked discussions. The investigation of the local underdensity is more gradual, requiring years of data accumulation and careful analysis, but it is progressing steadily. Papers have been published presenting updated measurements of the local matter density, comparisons to simulations, and implications for cosmological parameters. The picture is becoming clearer, and with each new data set, the confidence in the underdensity's reality grows. Yet confidence is not the same as certainty. Science operates on probabilities, not absolutes. Even the best established theories are provisional, subject to revision if new evidence emerges. The local underdensity could still turn out to be less significant than it currently appears, if future observations reveal systematic errors in the current measurements, or if simulations with better physics show that such voids are more common. Alternatively, it could turn out to be even more significant if the underdensity is deeper or larger than current estimates suggest. The only way to know is to keep observing, keep analyzing, and keep questioning. This iterative process is the essence of the scientific method. We make observations, form hypotheses, test predictions, and refine our understanding. The process is never finished because there are always more observations to make, more hypotheses to test, more predictions to refine. The goal is not to reach a final answer, but to approach truth asymptotically, getting closer with each iteration. The local underdensity is a case study in this process, a problem that has moved from speculation to serious investigation as the data has improved. One might ask, does it matter? Does it matter if we live in an underdense region? For practical purposes, the answer is no. The underdensity does not affect our daily lives, our technology, or even most of astronomy. The stars we see in the night sky, the planets in our solar system, the galaxies we study with telescopes, all would be the same whether we are in a void or not. The underdensity is a cosmological effect, relevant only when we try to understand the universe as a whole, its history, its composition, its fate. But for those who care about understanding the universe, it matters a great deal. Cosmology is driven by the desire to answer fundamental questions. Where did we come from? What is the universe made of? How will it end? These questions may not have practical applications, but they touch something deep in the human psyche. We want to know our place in the cosmos, to understand the context of our existence. The local underdensity, if confirmed, tells us that our place is less typical than we thought, that the view from Earth is colored by our location in a rare region. This does not diminish the grandeur of the universe, but it does change how we interpret what we see. It also has implications for the search for extraterrestrial life. If observers are more likely to arise in certain types of regions, then understanding the properties of those regions could guide the search. For instance, if life is more common in regions of average density, then our location in an underdense region might make us atypical, and the galaxy would be teeming with life that we have not yet detected, because we are looking from an unusual vantage point. Conversely, if life is equally likely in all regions, then the underdensity is irrelevant to astrobiology. These are speculative connections, but they illustrate how cosmological findings can ripple through other fields. Another implication involves the interpretation of future observations. As telescopes become more powerful and surveys more comprehensive, we will measure the properties of the universe with increasing precision. If we do not account for the local underdensity, those measurements will carry systematic biases that could lead us astray. For instance, future measurements of the dark energy equation of state might suggest that dark energy is evolving with time, when in fact the apparent evolution is due to our location in a void. Accounting for the underdensity is essential for avoiding such pitfalls and ensuring that our interpretations are correct. The technical challenge of accounting for the underdensity involves modeling its effects on observables. Light from distant objects passes through our region on its way to us, and the underdensity affects that light in subtle ways. Gravitational lensing by the matter along the line of sight bends and magnifies the light, changing the apparent brightness and position of distant sources. The expansion rate in our region differs slightly from the global average, affecting redshifts and distance measurements. These effects are small, typically a few percent, but they are not negligible for precision cosmology. Modeling them requires detailed knowledge of the matter distribution along every line of sight, which is exactly what James Webb and other surveys are providing. The modeling itself is computationally intensive. Researchers use ray tracing techniques, where they simulate the path of light through a simulated universe, accounting for all gravitational deflections and redshift effects. By comparing the observed light to the simulated light, they can infer the properties of the matter distribution and correct for its effects. This process is repeated for many different models and parameters, searching for the best fit to the data. The result is a set of corrected cosmological parameters that account for the local underdensity and provide a more accurate picture of the global universe. The corrected parameters may differ from the uncorrected ones in important ways. The Hubble constant, for instance, might be lower than the local measurement suggests once the underdensity is accounted for. The matter density might be higher. The dark energy equation of state might be closer to the simplest value of -1, corresponding to a cosmological constant. These corrections could resolve existing tensions and bring different measurements into agreement, which would be a major success for the standard model. Alternatively, the corrections might not be enough, and residual tensions might remain, pointing to new physics. We are in a period of active investigation, where the answers are not yet clear. This is an exciting time for cosmology, a time when fundamental questions are being addressed with cutting-edge tools. James Webb is at the forefront of this effort, providing the data that will shape our understanding for decades to come. But the telescope is not alone. It is part of a broader ecosystem of instruments and missions, each contributing its unique capabilities. Together, they form a comprehensive observational program that is mapping the universe in unprecedented detail. Ground-based telescopes, such as the Keck telescopes, the Very Large Telescope, and the upcoming Extremely Large Telescopes, provide complementary data with different strengths. They can observe large areas of the sky quickly, something space telescopes struggle with due to their smaller fields of view. They can also achieve very high spectral resolution, allowing detailed studies of galaxy kinematics and chemical compositions. The trade-off is that ground-based telescopes must contend with Earth's atmosphere, which absorbs and distorts light, but adaptive optics systems are mitigating this limitation. Space telescopes like Hubble, Chandra, and the upcoming Nancy Grace Roman Space Telescope each cover different wavelengths and have different capabilities. Hubble remains a workhorse for optical and ultraviolet observations, providing sharp images and spectra. Chandra observes in X-rays, revealing hot gas in galaxy clusters and active galactic nuclei. Roman, set to launch in the late 2020s, will have a field of view 100 times larger than Hubble's, making it ideal for wide-area surveys of the type needed to map large-scale structure. Radio telescopes, such as the Atacama Large Millimeter Array and the Square Kilometer Array, observe at even longer wavelengths, probing cold gas and the cosmic microwave background with high precision. ALMA, already operational, has revolutionized the study of star formation and galaxy evolution. SKA, under construction, will be the most sensitive radio telescope ever built, capable of detecting faint signals from the early universe and mapping the distribution of hydrogen gas, a tracer of matter. All these instruments feed data into the same framework, the standard cosmological model, and each provides a different piece of the puzzle. The power of modern cosmology lies in this multi-wavelength, multi-instrument approach. No single observation is definitive, but the combination of many observations from many instruments creates a robust, cross-checked picture. When all the pieces fit together, confidence is high. When they do not, it signals that something is not understood, and it drives further investigation. James Webb's contribution is unique because of its infrared sensitivity and its position outside the atmosphere, but it is most powerful when combined with data from other sources. For instance, Webb can identify high redshift galaxies, and then ground-based telescopes can follow up with detailed spectroscopy. Webb can measure the distribution of galaxies in the local universe, and then gravitational lensing surveys can map the dark matter distribution for comparison. Webb can observe distant supernovae, and then radio telescopes can measure the expansion rate through independent methods. This synergy multiplies the scientific return and ensures that conclusions are well-founded. As the data accumulates, patterns emerge that point toward answers. The local underdensity is one such pattern, a signal that has strengthened as the observations have improved. Whether it ultimately leads to a revolution in cosmology or refinement of the existing model remains to be seen, but the investigation itself is transformative. It forces us to confront the limits of our knowledge, to question our assumptions, and to think more deeply about what we can and cannot infer from observation. There is a broader lesson here about the nature of science. Science is not a collection of facts, but a process of inquiry. It is not about achieving certainty, but about reducing uncertainty. It is not about proving theories true, but about testing them rigorously and discarding those that fail. The local underdensity is a reminder that even well-established principles like the cosmological principle are provisional, subject to empirical test. If the test reveals deviations, we must adapt. This adaptability, this willingness to revise in the face of evidence, is science's greatest strength. The human element is also part of the story. Behind every observation, every simulation, every analysis, there are people, researchers driven by curiosity and a desire to understand. They spend years designing instruments, writing proposals, analyzing data, debating interpretations. The process is collaborative and competitive, with groups around the world working on the same problems, sometimes cooperating, sometimes racing to publish first. This dynamic drives progress, pushing the field forward faster than any single group could manage alone. The funding of science, the politics of large projects, the training of new generations of researchers all play roles in how the field develops. James Webb itself is a product of this system, the result of decades of planning, engineering, and negotiation. It represents an investment not just in hardware but in knowledge, in the collective human endeavor to understand the cosmos. When the telescope delivers data that challenges our assumptions, it justifies that investment, proving that the pursuit of fundamental knowledge has value beyond immediate application. Looking forward, the next decade promises to be a golden age for cosmology. James Webb will continue to observe, adding to its already impressive dataset. The Vera Rubin Observatory will begin operations, surveying the sky night after night and building a movie of the cosmos, tracking changes and cataloging billions of objects. The square-kilometer array will come online, opening the radio sky to unprecedented scrutiny. The Nancy Grace Roman Space Telescope will launch, complementing Webb with wide-field infrared surveys. And the extremely large telescopes on the ground will achieve first light, bringing the universe into focus as never before. With this armada of instruments, the local underdensity will be mapped in exquisite detail. Its boundaries will be traced, its depth measured, its history reconstructed. Other voids will be found and characterized, allowing for statistical comparisons. The effects of the underdensity on cosmological measurements will be modeled and corrected, and the theoretical framework will be tested with a rigor that was previously impossible. We may also discover entirely new phenomena, things we have not yet imagined. The history of astronomy is full of serendipitous discoveries, observations that revealed something unexpected and opened new fields of study. Pulsars, quasars, gamma-ray bursts, dark energy, all were surprises. James Webb and the other telescopes of this era are poised to deliver more surprises, and some of them may be related to the local underdensity or to the broader questions about large-scale structure and homogeneity. One possibility is the detection of even larger structures, beyond the supervoid scale. Theoretical work has suggested that under certain conditions, structures on scales approaching the horizon could exist, though they would be subtle and hard to detect. If such structures are found, they would force a major rethinking of cosmology, as they would violate the assumptions of homogeneity even more severely than the local underdensity. James Webb's reach extends far enough that such structures, if they exist, might leave signatures in the data. Another possibility is the discovery of variations in fundamental constants across the universe. There have been hints, tentative and controversial, that the fine structure constant, or the proton-to-electron mass ratio, might vary slightly in different regions or at different times. If such variations are real, they would have profound implications, suggesting that the laws of physics themselves are not uniform. This is a radical idea, far outside the mainstream, but it is the kind of question that future observations could address. James Webb, through precise spectroscopy of distant quasars, can measure the ratios of atomic transition wavelengths, which depend on fundamental constants, and test for variations. These are speculative directions, but they illustrate the open-ended nature of the inquiry. We do not know what we will find, and that is part of the excitement. The universe has a way of surprising us, of revealing complexity and beauty where we expected simplicity or uniformity. The local underdensity is one such surprise, a feature of the universe that we did not anticipate but that, once recognized, demands explanation. The search for that explanation is driving some of the most interesting work in cosmology today. Let us return to the core mystery. We live in a region that appears to be significantly underdense compared to the cosmic average. This underdensity extends for hundreds of millions of light-years, affecting our measurements of the expansion rate, the matter density, and other cosmological parameters. James Webb Space Telescope has provided data that reinforces the reality of this underdensity, mapping the distribution of galaxies with unprecedented clarity and reach. The question now is what to make of it. Is it a statistical fluke, a rare fluctuation that we happen to observe because we can only observe from where we are? This explanation is statistically valid, but requires accepting a coincidence. We live in a 1 in several hundred or 1 in several thousand region, depending on the exact numbers. Coincidences happen, and in an infinite or very large universe, every rare event occurs somewhere. But it is unsettling to find ourselves in such a region, and it raises the question of observer bias and whether our measurements are representative. Is it a sign that the cosmological principle is not strictly true, that the universe is more inhomogeneous on large scales than we thought? This would require rethinking the foundation of modern cosmology, but it would not necessarily overturn the Big Bang model or the broad framework of structure formation. It would mean that the universe is more complex, with larger structures and greater variability than the simplest models predict. This complexity might arise from features in the inflationary potential, from non-Gaussian initial conditions, or from dynamical processes in the late universe that we have not fully understood. Is it an indication that we need new physics, that dark energy or dark matter behaves differently than we have assumed? This is the most radical possibility, but it cannot be ruled out. If the underdensity is too large or too deep to be explained by known processes, it might point to modifications of gravity, to new types of fields or particles, or to interactions between dark matter and dark energy that we have not considered. Such new physics would need to be consistent with all other observations, a stringent requirement that limits the possibilities. But the history of science shows that major discoveries often come from anomalies that do not fit the existing framework. Or perhaps it is a combination of these factors, a complex interplay of statistical rarity, large-scale inhomogeneity, and subtle new physics. Disentangling these factors requires more data, better simulations, and deeper theoretical insights. James Webb is providing the data, and researchers are working on the simulations and the theory. Over time, the picture will become clearer, and we will move from speculation to understanding. In the meantime, we must live with uncertainty. This is not a comfortable position, but it is the position of science at the frontier. Certainty comes only with hindsight, after the questions have been answered and the textbooks rewritten. In the present, we grapple with incomplete data, competing hypotheses, and the humbling recognition that the universe is under no obligation to make sense to us. It simply is, and our task is to observe, to measure, to reason, and to infer what we can from the evidence available. The emotional weight of this inquiry should not be underestimated. For many cosmologists, the cosmological principle is more than a technical assumption. It is a philosophical stance, a statement about the democracy of the cosmos, the idea that no place is special and that the universe treats all observers equally. To find that we live in an unusual region challenges this egalitarian view and introduces an element of contingency. Our measurements, our theories, our understanding of the universe, all are shaped by the accident of our location. This is not a comfortable realization, but it is an important one. It also serves as a reminder of the limits of human knowledge. We are small creatures on a small planet, trying to understand a universe that is vast beyond comprehension. We have made remarkable progress, building telescopes that can see across billions of light years, developing theories that can predict the behavior of matter and energy under extreme conditions, and constructing a coherent narrative of cosmic history from the Big Bang to the present. But there is still much we do not know, and there may always be aspects of the universe that remain beyond our grasp. The local underdensity is a case in point. It is a feature of the universe that we have only recently recognized, despite decades of observation and analysis. It may take decades more to fully understand it, and even then, there will be other mysteries waiting to be uncovered. This is the nature of science, an endless frontier where each answer leads to new questions. James Webb. Space Telescope is a tool in this ongoing exploration, a powerful instrument that extends our reach and sharpens our vision. Its observations are not the final word, but a contribution to a larger conversation, a conversation that spans generations and continents, involving thousands of researchers and countless hours of labor. The telescope has already delivered transformative results in its short operational life, and it will continue to do so for years to come. Its impact on our understanding of the universe and of our place within it will be felt long after the mission ends. The investigation of the local underdensity is one thread in a larger tapestry of cosmological inquiry. Other threads include the nature of dark matter, the properties of dark energy, the origin of the matter-antimatter asymmetry, the formation of the first stars and galaxies, the evolution of large-scale structure, and the ultimate fate of the universe. Each of these questions is being addressed by observations from James Webb and other telescopes, by theoretical work, and by simulations. Together, they form a comprehensive program of research aimed at understanding the universe in its entirety. The answers to these questions may come quickly, or they may take decades. Some may be answered definitively, while others may remain uncertain or unresolved. But the pursuit is worthwhile, not just for the knowledge it generates, but for the process itself. The act of asking questions, of seeking evidence, of testing hypotheses, is what defines us as a species. We are curious, we are driven to explore, and we are capable of remarkable insights when we apply our intellect and our tools to the study of nature. The local underdensity, if confirmed, will stand as a monument to this process. It is a discovery that emerged from careful observation, rigorous analysis, and a willingness to question assumptions. It challenges our understanding and demands explanation. And it reminds us that the universe, for all its grandeur and beauty, does not always conform to our expectations. It is stranger, more complex, and more wondrous than we imagined. As we continue to probe the cosmos, as James Webb and future telescopes push the boundaries of observation, we will encounter more such surprises. Each one will teach us something, not just about the universe but about ourselves, about our capacity for understanding and our place in the grand scheme of existence. The local underdensity is one chapter in this ongoing story, a chapter that is still being written. We do not yet know how it will end, but we are privileged to witness it unfold. In the vastness of space, in the depths of time, in the interplay of matter and energy, we find questions that have no easy answers. The James Webb Space Telescope has shown us that we live in a region that, by all statistical measures, should not exist, or at least should not contain us as observers. This revelation is disquieting and profound. It forces us to reconsider our assumptions, to refine our models, and to accept that the universe is more complex than we thought. Yet this complexity is also a source of awe. The universe is not a simple, uniform expanse but a richly textured landscape of structure and void, of cluster and filament, of galaxy and star. We are part of this landscape, inhabitants of a region that is rare and perhaps special, at least in the statistical sense. Whether this specialness has deeper meaning is a question we cannot yet answer, but the search for meaning is itself a human endeavor, one that gives purpose to our exploration of the cosmos. The data from James Webb will continue to flow, the analysis will continue to progress, and the understanding will continue to evolve. We stand at a moment in history when the tools are powerful enough to address fundamental questions, when the data is rich enough to test bold hypotheses, and when the community is large and collaborative enough to tackle the hardest problems. The investigation of the local underdensity is emblematic of this moment, a challenge that requires the best of our observational, theoretical, and computational capabilities. In the end, the question of whether we live in a region that should not exist is a question about probability, about interpretation, and about the nature of the cosmos itself. It is a question that touches on the deepest issues in cosmology and philosophy, and it is a question that James Webb is helping us to answer, not with simple certainty but with the kind of nuanced, evidence-based understanding that is the hallmark of good science. We may never achieve complete certainty about our cosmic location and its implications, but we can achieve clarity, we can achieve consistency, and we can achieve a deeper appreciation for the universe we inhabit. The local underdensity, whether it is a fluke, a feature, or a clue to new physics, is a gift. It is an opportunity to learn, to grow, and to refine our understanding. It is a reminder that the universe still has secrets to reveal, and that we, with our telescopes and our curiosity, are capable of uncovering them. The journey is far from over. The data is still coming in, the debates are still ongoing, and the conclusions are still uncertain. But the direction is clear. We are moving toward a more complete picture of the universe, one that accounts for our location, corrects for our biases, and recognizes the full complexity of cosmic structure. James Webb Space Telescope is our guide on this journey, illuminating the path with its infrared eyes and revealing the universe in all its strange and beautiful detail. As we look out into the cosmos, as we trace the filaments and voids, as we measure redshifts and count galaxies, we are doing more than just collecting data. We are engaging with the fundamental questions of existence. Where do we come from? What is the nature of reality? Are we alone? These questions have driven human inquiry for millennia, and they continue to drive us today. The tools have changed, the methods have improved, but the questions remain. The local underdensity is a piece of the puzzle, a clue that might help us answer these questions. It tells us that the universe is not uniform, that our location is not typical, and that the view from Earth is colored by the region we inhabit. This knowledge is both humbling and empowering. Humbling because it reminds us of our limitations, of the fact that we can only observe from one place and one time. Empowering because it shows that we can recognize our biases, account for them, and still extract meaningful truths about the cosmos. The work continues. Researchers around the world are analyzing James Webb data, running simulations, writing papers, and debating interpretations. Conferences are held, collaborations are formed, and ideas are exchanged. The scientific community is a living, dynamic entity, constantly adapting and evolving as new evidence emerges. The investigation of the local underdensity is part of this larger process, a thread that connects observers, theorists, and simulators in a common quest for understanding. In the quiet moments, when the data has been analyzed and the papers have been published, there is a sense of wonder that transcends the technical details. We live in a universe that is vast, ancient, and structured in ways we are only beginning to comprehend. We have built instruments that can peer across billions of light years and billions of years, revealing the history and architecture of the cosmos. And we have discovered that our own neighborhood, the region of space we call home, is unusual, a statistical outlier in the cosmic distribution. This discovery does not diminish the universe. If anything, it enriches it, adding layers of complexity and mystery. It challenges us to think harder, to look deeper, and to question more rigorously. It reminds us that the universe does not owe us simplicity or convenience, and that the truth, whatever it may be, must be earned through careful observation and thoughtful analysis. James Webb Space Telescope has given us the means to pursue this truth. Its images and spectra are not just data points but windows into the cosmos, glimpses of a reality that exists far beyond our everyday experience. Through these windows, we see galaxies forming, stars dying, and structures evolving, and we see, in the distribution of those galaxies and structures, the signature of our own location, the imprint of the void we inhabit, the void we call home. It is a poetic phrase, but it captures something essential about our situation. We are surrounded by emptiness, by a region where matter is sparse and galaxies are few. Yet within this emptiness, we have emerged, we have built civilizations, and we have turned our eyes to the sky to ask why. The answer, if there is one, lies in the data, in the simulations, in the theories that we construct to make sense of what we observe. As the years pass and the data accumulates, the picture will become clearer. The boundaries of the void will be mapped, its properties quantified, its origins traced. The biases it introduces into our measurements will be corrected, and the cosmological parameters will be refined. The tensions between different observations may be resolved, or they may point to new physics. Either way, we will have learned something, and our understanding will have deepened. This is the promise of James Webb and the broader program of observational cosmology. It is not a promise of easy answers or quick resolutions, but a promise of progress, of movement toward truth. Each observation, each analysis, each simulation brings us closer to a comprehensive understanding of the universe, its history, its structure, and its future. The local underdensity is one piece of that understanding, a piece that has only recently come into focus but that will play a role in shaping our cosmological worldview for decades to come. In the end, the question is not whether we live in a region that should not exist. The region exists, we live in it, and that is a fact. The question is what this fact implies about the universe, about the processes that shaped it, about the statistical framework we use to interpret observations, and about the nature of physical law. These are profound questions, and they do not have simple answers. But they are the right questions to ask, and the pursuit of answers is a worthy endeavor. James Webb Space Telescope has shown us the way forward. It has provided the data, the clarity, and the reach to tackle these questions with rigor. The observations are in, the analysis is underway, and the conclusions are beginning to emerge. We live in a region that is underdense, that is large, and that is affecting our view of the cosmos. This is not a comfortable truth, but it is a truth nonetheless, and it must be reckoned with. The cosmos does not care about our comfort. It is vast, indifferent, and governed by laws that operate on scales far beyond human comprehension. Yet we, small and transient as we are, have the capacity to study it, to understand it, and to appreciate its grandeur. We have built telescopes that can see across the universe, and we have developed theories that can explain what we see. This is an extraordinary achievement, a testament to human curiosity and ingenuity. The local underdensity is a reminder that the universe still has surprises in store, that our understanding is incomplete, and that the journey of discovery is ongoing. It is a challenge and an opportunity, a puzzle that demands solution and a mystery that invites exploration. James Webb has handed us the pieces, and now it is up to us to assemble them, to see the picture they form, and to understand what that picture tells us about the cosmos and our place within it. The stars overhead, the galaxies beyond, the filaments and voids that structure the universe, all are part of a grand tapestry that we are only beginning to see in full. The void we call home is one thread in that tapestry, a thread that is unusual, that is significant, and that is shaping our understanding in ways we are only now appreciating. The work of disentangling this thread, of understanding its origins and implications, is the work of a generation, and it is work that will define the future of cosmology. As we stand on the edge of this new understanding, as we grapple with the implications of living in a statistical anomaly, we are reminded of the fragility and the power of knowledge. Knowledge is fragile because it is always provisional, always subject to revision in the light of new evidence. But knowledge is powerful because it allows us to see beyond ourselves, to understand the universe in ways that transcend our immediate experience, and to connect with a reality that is larger and more wondrous than we can fully grasp. The data from James Webb will be analyzed for years, perhaps decades. New insights will emerge, new questions will be asked, and new mysteries will be uncovered. The local underdensity is just one chapter in this ongoing story, but it is a chapter that matters, a chapter that has the potential to reshape our understanding of the cosmos. We are living through this chapter, witnessing it unfold in real time, and that is a privilege and a responsibility. We owe it to ourselves and to future generations to pursue this inquiry with rigor and honesty, to follow the evidence wherever it leads, and to accept the conclusions even if they are uncomfortable or unexpected. Science is not about confirming what we already believe. It is about discovering what is true, regardless of our preconceptions. The local underdensity may be inconvenient. It may complicate our models. It may force us to reconsider cherished principles. But if it is real, we must accept it and work to understand it. James Webb Space Telescope has given us the tools to do that work. The observations are transformative, the capabilities are unprecedented, and the potential for discovery is immense. We are at a turning point in cosmology, a moment when long-standing questions are being addressed with new data and new methods. The investigation of the local underdensity is central to this moment, a test case for how we handle anomalies, how we integrate data from multiple sources, and how we refine our theories in the face of evidence. The journey ahead is uncertain. We do not know what we will find, and we do not know how the story will end. But we know that the pursuit is worthwhile, that the questions are important, and that the process of inquiry is itself valuable. As we map the void, as we measure its properties, as we simulate its formation and evolution, we are engaging with the universe at the deepest level, asking fundamental questions about structure, homogeneity, and the nature of existence. In the darkness between the stars, in the vast empty spaces that separate the galaxies, we find not absence, but presence, not void, but structure, not simplicity, but complexity. The universe is a place of infinite variety, and we are only beginning to explore its richness. James Webb is our vehicle for that exploration, a machine of exquisite precision and sensitivity, designed to reveal what has been hidden and to answer what has been asked. The void we call home is no longer a mystery shrouded in ignorance. It is a feature of the universe that we can observe, measure, and study. It is a challenge to our understanding, yes, but it is also an opportunity to learn, to grow, and to deepen our connection with the cosmos. The work continues, the data flows, and the story unfolds. We are part of that story, observers and participants, witnesses to the revelation of cosmic truth. And in that revelation, in the careful accumulation of evidence and the rigorous testing of hypotheses, we find something more than just knowledge. We find meaning, we find purpose, and we find a connection to something larger than ourselves. The universe is vast and we are small, but through science, through observation, through the relentless pursuit of understanding, we bridge that gap. We reach out across the void, across the billions of light years, and we touch the fabric of reality itself. This is the legacy of James Webb, and this is the promise of cosmology. The investigation of the local underdensity is part of that legacy, a contribution to the ongoing human endeavor to understand the universe and our place within it. The telescope has shown us that we live in a region that is unusual, that challenges our assumptions, and that demands explanation. And in doing so, it has given us a gift, the gift of new questions, new data, and new possibilities for discovery. The cosmos awaits, vast and mysterious, filled with wonders we have yet to imagine. James Webb is our guide, our window, our instrument of inquiry. Through its observations, we see the universe not as we wish it to be, but as it is, in all its complexity and strangeness. And we see that we are part of that universe, inhabitants of a rare and remarkable region, explorers standing on the edge of the unknown, looking out into the dark and asking why. The answer, whatever it may be, is worth seeking. And the journey, with all its challenges and uncertainties, is worth taking. We live in a region that should not exist, or so the statistics suggest. But here we are, and here the universe is, and the meeting of the two is the story of cosmology, the story of James Webb, and the story of our quest to understand the void we call home.